Hello there and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath us and travel toward a place that appears at first to contain almost nothing at all. It is a great cosmic void, an enormous dark basin in the distribution of galaxies surrounded by brighter walls and delicate filaments that stretch across distances too large for any ordinary map. From far away, the void can look like a missing piece of the universe, as though someone quietly removed the galaxies and forgot to fill the gap. But a cosmic void is not a hole cut through space, and it is not a chamber with a black wall around it. Space continues through the region. Light continues through it. Gravity continues working with its usual refusal to take a holiday. The real question is subtler when astronomers identify one of these immense underdense regions. What exactly have they found, and what might still be waiting inside? From the room around you, the universe does not look web-shaped. Through a window, the night sky appears scattered with separate points of light, each one placed against a smooth darkness. Even photographs of distant galaxies can preserve that impression, showing isolated spirals and glowing ellipses suspended in black space. Yet those images flatten a three-dimensional universe onto a two-dimensional sky. To uncover the larger pattern, astronomers measure not only where galaxies appear, but also how their light has been stretched as the universe expands. With enough measurements, they can build a map in depth. On that map, galaxies are not sprinkled evenly. They gather into groups and clusters. Clusters lie along broad walls, and those walls are joined by long filaments. Between them are regions with far fewer galaxies than average. These are cosmic voids. They may span distances so large that even light requires hundreds of millions of years to cross the greatest examples. Still, the important idea is simple. A void is recognized by comparison. It is not defined by having nothing. It is defined by having much less. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you like the video and subscribe to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. And for tonight's question, would you rather discover a hidden galaxy inside the void or learn why the void became so enormous? There is no wrong answer. One choice follows the few lights that remain. The other follows the matter that slowly left. Before long we will do both. For now, get comfortable and allow the room to become a little quieter. Let your shoulders rest and let the details pass without any need to hold on to them. There will be no test waiting at the center of the void. You can follow every step or simply let the scale of the journey move gently through the background while you settle into sleep. As we approach this dark region, we can carry a few questions with us. Where does the bright cosmic web end and the void begin? Is there a true boundary, or only a gradual thinning of galaxies? How empty can a region become while still containing matter? What kinds of galaxies manage to survive so far from crowded clusters? How can astronomers measure something that is mainly noticed by what is missing? And if a void contains fewer objects, can that absence reveal something important about the history of the universe? We will take them slowly, one at a time. Our starting point is the cosmic web itself. Imagine pulling far away from the Milky Way until our galaxy becomes one faint point among many, then continuing outward until individual galaxies begin to merge into a wider pattern. Dense clusters would appear as bright knots. Long chains of galaxies would stretch between them. Broad sheets would curve through space, and around those sheets would open immense darker regions. The result might resemble a map of towns and illuminated roads seen at night with wide rural spaces lying between them. It is a useful picture, but only a beginning. Galaxies are not fixed lamps placed on a permanent road network. The cosmic web grew over billions of years as gravity amplified small differences in the early distribution of matter. Regions that began with slightly more matter attracted still more. Regions that began with slightly less matter lost ground, in a very literal gravitational sense. Matter gathered more efficiently elsewhere, and the underdense regions gradually became emptier relative to their surroundings. The web and the voids grew together. One cannot be understood without the other. Now let us choose one of those dark basins and begin moving toward it. Behind us, the cosmic web is crowded by universal standards. Galaxy groups, filaments, and glowing clusters mark the landscape. Ahead, the lights become less frequent, yet there is no sign announcing that the void begins here. No shell passes over us. No physical curtain closes behind us. Instead, the change is gradual. Large groups give way to smaller associations. The distance between bright galaxies increases. The surrounding filaments become thinner, and the darkness occupies more of the view. Astronomers can draw a boundary around this region, but that boundary depends on how the map was made, which galaxies were included, and what mathematical method was used to identify the underdensity. Another survey might draw the outline slightly differently. The universe, as usual, has produced the landscape without supplying the border paperwork. For now, remember only this: we have not entered absolute emptiness. We've entered a region where the universe has become unusually sparse, and as the last bright ridge fades behind us, the next step is to discover how astronomers decide just how empty this darkness really is. A cosmic void does not begin at a wall. It begins when the crowd thins enough for the absence to become part of the landscape. As we continue forward from the bright filament behind us, the change is easy to miss from one moment to the next. A galaxy still glows in the distance. Then another appears farther away than the last. Small groups become rarer. The broad, luminous ridge behind us grows narrower, while the darkness ahead expands until it seems to occupy almost everything. If we could place a marker at every galaxy and then step back, the pattern would reveal itself more clearly. The markers would be tightly packed near the surrounding walls, more widely separated near the rim, and sparsest toward the interior. Yet at no point would space announce that we had crossed from one official region into another. The boundary exists because astronomers compare densities across enormous volumes and decide where a significant underdensity begins. It is a useful boundary. It is not a physical one. One way to picture this transition is to imagine leaving a city late at night. Near the center, buildings stand close together, and windows fill the streets with light. Farther out, the buildings become lower, the roads quieter, and the spaces between houses wider. Eventually, the city gives way to open countryside, but there may be no single moment when every observer agrees that the city has ended. One map may place the boundary at the last dense neighborhood, another may include the scattered suburbs, a third may use an administrative line that the landscape itself does not care about. A cosmic void behaves in a similar way. Its rim is defined by the changing distribution of matter, not by a fence or surface. The analogy has limits, of course. Galaxies are not houses, and cosmic filaments were not designed by a planning office with unusually generous spacing. Still, the comparison captures the central idea. The edge of a void is a transition from greater density to lesser density stretched across a region rather than compressed into a line. Astronomers often describe this transition using a density profile. Imagine measuring the amount of matter in a series of broad nested shells centered on the void. Near the middle, the average density may be very low. Moving outward, the density generally rises. In some voids, it climbs gradually until it reaches the cosmic average. In others, it rises beyond the average and forms a denser ridge around the underdense interior. This ridge may contain galaxies groups, and filaments that accumulated as matter moved away from the void's center and towards stronger gravitational structures. From far enough away, the combination can resemble a shallow basin surrounded by a raised rim. But this should not be mistaken for a perfect bowl. Real voids are irregular. Their centers may be offset. Their edges may fold around neighboring filaments. Several smaller underdense regions may overlap, and one side may be bordered by a rich cluster, while another fades gently into a quieter sheet of galaxies. The diagrams are neat because diagrams are cooperative. The universe is under no similar obligation. This irregularity matters because different methods can identify different voids within the same galaxy survey. One technique may search for nearly spherical regions containing very few galaxies. Another may treat the galaxy distribution like a landscape and locate broad basins between dense ridges. A third may examine the underlying matter field in a computer simulation where dark matter can be tracked even when no bright galaxy marks its location. Each method asks a slightly different question. Is the void the largest nearly empty sphere that can fit between galaxies? Is it the entire basin enclosed by surrounding structures? Is it an underdensity in visible galaxies, dark matter, or total matter? These definitions often overlap, but they are not identical. As a result, the same region may receive different center shapes or effective sizes depending on the catalogue. This does not mean astronomers have failed to locate it. It means that a cosmic void is not a simple object like a planet with a surface. It is a feature in a continuous distribution, and continuous landscapes rarely cooperate with perfectly sharp labels. The surrounding ridge also tells us something about the void's history. A large mature void may have pushed much of its matter outward, in the sense that gravity drew material more effectively toward the denser structures around it. The central region did not repel matter. There is no hidden engine at the middle blowing galaxies away. Instead, matter in the early universe responded to small differences in density. Where slightly more matter gathered, gravity became stronger and drew in still more. Where slightly less matter existed, growth proceeded more slowly, and material was gradually redirected toward neighboring overdensities. Over billions of years, the contrast deepened. The underdense region became emptier relative to the universe around it, while walls and filaments became more pronounced. In some cases, the material surrounding a void may be dense enough to form a distinct ridge. In others, the void is part of a larger underdense environment, and the transition outward is smoother. The rim therefore preserves a quiet record of motion, not just a border on a map. As we travel farther inward, the bright structures behind us begin to look less like a wall and more like a distant horizon of scattered light. Ahead, a few galaxies remain, but they are separated by enormous distances and connected perhaps by structures too faint to see directly. We have crossed the rim only in the practical sense that the surrounding density has fallen below the level chosen by a particular map or method. Another astronomer, using another catalogue, might tell us the crossing happened earlier or later. Both could still be describing the same broad underdensity. For now, the most important image is not a doorway, but a slope-crowded space becoming sparse, dense structure, thinning into a wide basin, and the cosmic average slowly receding behind us. The next question is no longer where the void begins. It is how far below average the interior truly falls, and what the word empty can reasonably mean in a universe where even the darkest region still contains something. Empty is not a quantity until we decide what we're comparing it with. Now that we have crossed the gradual rim of the void, the galaxies around us seem scattered almost carelessly through the darkness. One faint point lies ahead, another rests far to one side. Between them is an interval so large that the word distance begins to feel rather underprepared for the job. Yet astronomers cannot simply look at this scene and declare it empty. They must compare it with an equivalent region elsewhere in the universe. How many galaxies would normally occupy a volume this large? How much matter would be expected if the region matched the cosmic average? How does the density change as we move from the centre toward the surrounding filaments? Only after those comparisons can the void be described as underdense. This is the first important answer. Cosmic emptiness is relative. The void contains less matter than the average region of the same size, sometimes dramatically less, but less is not the same as none. Imagine an enormous theatre in which nearly every seat is unoccupied. From the stage, the room may appear deserted, yet a few people remain in distant rows. There are also seats, railings, carpets, dust, warm air, and the building itself. Counting the audience tells us something useful, but it does not provide a complete inventory of the room. Galaxy surveys face a similar limitation. Galaxies are the most convenient visible markers of large-scale structure, so astronomers often use them to trace where cosmic matter is concentrated. But galaxies are not identical particles distributed evenly through space. Bright galaxies are easier to detect than faint ones. Massive galaxies tend to occupy different environments from small galaxies. Some collections of galaxies trace dense regions more strongly than others. A map made only from the brightest objects may therefore make a void look emptier, steeper, or larger than a deeper map that includes dimmer galaxies. The visible audience changes with the sensitivity of the survey. The cosmic theatre remains the same. To measure the structure more carefully, astronomers can combine many voids of similar type and study their average density profile. Picture each void reduced to a common scale placed gently on top of the others and aligned around an estimated centre. Individual irregularities begin to soften while the shared pattern becomes clearer. Near the central region, the average number of galaxy traces is low. Moving outward, the density usually rises, sometimes passing through a crowded ridge before settling toward the wider cosmic average. This process is called stacking, although nothing physical is being piled up in space. It is a statistical method for revealing a signal that may be difficult to see in one oddly shaped void. The resulting profile is useful, but it is not the portrait of every individual underdensity. One void may be deep and broad, another may contain more internal structure. A smaller void inside a dense environment may look very different from a large void opening into another sparse region. Average landscapes are informative. They are also tidier than the places from which they were made. There is another complication. The density of visible galaxies is not automatically the same as the density of all matter. Most matter does not shine. Dark matter contributes to the gravitational structure of the region, while extremely diffuse ordinary gas may pass unnoticed between the few galaxies we can see. A place containing almost no bright galaxies may still contain dark matter, halos, thin gas particles and radiation. Conversely, one luminous galaxy does not mean that the surrounding volume has returned to average density. Astronomers therefore distinguish between the tracer field and the underlying matter field. The tracers are the objects used to draw the map. The matter field is the fuller distribution they are attempting to reconstruct. Computer simulations can follow dark matter through a modelled universe and compare its distribution with the galaxies expected to form within it. Gravitational lensing can also provide a statistical view of total matter by measuring how foreground structure slightly alters the apparent shapes of distant galaxies. These methods do not reveal every particle. They help check whether the missing light corresponds to genuinely missing mass. This is why no single emptiness percentage should be carried from one cosmic void to every other. The result depends on which objects were counted, how faint the survey could see how the void was selected, what distance from its center was measured, and whether the discussion concerns galaxies or total matter. Even the center can be troublesome. An irregular void may not possess one obvious geometric middle. A center defined by the surrounding galaxies may differ from the lowest point in the reconstructed matter density. Place the measurement slightly elsewhere and the profile changes. Use rare bright galaxies as tracers, and large stretches may contain no detected object at all. Include smaller and fainter galaxies, and some of those stretches acquire points of light. None of this makes the void imaginary. It reveals that empty is an observational description built from limited samples. Scientists must state what was measured before the number can mean anything. The universe is not being evasive. It simply neglected to organize itself for convenient spreadsheet use. From our imagined position near the interior, the darkness now carries several layers of meaning. There is the emptiness our eyes would report because very few bright galaxies interrupt the view. There is the low galaxy density recorded by a survey. Beneath that lies a reduced but still present distribution of ordinary matter and dark matter, and beneath the measurements lies a final region of uncertainty, containing objects too faint gas, too diffuse, or structures too small for the present map to reveal clearly. We can therefore answer the question without forcing it into a single number. A cosmic void is empty in comparison with the average universe, but it is not empty in the absolute sense. Its darkness is a deficit, not a perfect vacuum. And once we stop asking whether anything exists here, and begin asking what kinds of things remain, the few distant galaxies ahead become more than exceptions. They become our next guides. Isolated lights growing in one of the quietest environments the universe can provide. The deepest darkness of a cosmic void is not completely without lights. As we continue inward, one of those lights slowly separates itself from the background, becoming a faint galaxy, suspended at an enormous distance from the bright walls behind us. It may be a small spiral, a loose irregular system, or a dim collection of stars whose glow barely reaches the instruments searching for it. Around a crowded galaxy cluster, this object might seem unremarkable. Here it becomes a landmark. Galaxies inside voids are uncommon because the matter needed to build them was less abundant from the beginning, but uncommon does not mean impossible. Small concentrations of dark matter still formed inside the underdensity. Ordinary gas collected within some of those gravitational wells. Stars ignited, aged, and returned enriched material to their surroundings. A galaxy began to grow. It did not require a nearby cluster to grant permission. Gravity works locally as well as cosmically, and even in a region with far less matter than average, a sufficiently dense pocket can become a small island of structure. It is tempting to describe every void galaxy as young blue gas rich and untouched by the rest of the universe. The reality is quieter and more varied. Surveys often find that void populations contain many lower-mass star-forming galaxies, especially when compared with populations in dense clusters, where large red inactive galaxies are common. But much of that contrast arises because the environments contain different mixtures of galaxy masses and types. When astronomers compare a void galaxy with a galaxy of similar mass and structure, in a less extreme environment, some differences become modest. Void galaxies can be blue or red, active or quiet, orderly or disturbed. Some retain large reservoirs of atomic gas. Some form stars slowly across their disks. Others have already reduced their star formation. A galaxy's address matters, but it is not its complete biography. Mass, gas supply, internal structure, past interactions, and the activity of stars and black holes all participate. The cosmic postcode is influential. It is not especially good at filling out the entire form. The surrounding emptiness may nevertheless change the rhythm of a galaxy's life. In crowded regions, galaxies frequently pass near one another, exchange gas, distort their shapes, or lose material as they move through hot intracluster plasma. A void galaxy is less likely to experience those particular pressures. Major collisions may occur less often, and the supply of nearby companions may be smaller. This can allow a disk to evolve for long periods without repeated disturbance from massive neighbours. Gas may continue arriving along faint local streams, providing material from which new stars can form. Yet isolation does not guarantee calm. Inside the galaxy, massive stars still end their lives and stir the surrounding gas. Stellar winds still shape clouds. A central black hole may occasionally become active. Spiral patterns and bars can move material inward. Gravity within the disk can gather gas into new stellar nurseries. The void is peaceful only when viewed across millions of light years. Up close, an ordinary galaxy remains a busy piece of machinery, although one assembled in a very quiet district. As we approach the faint galaxy may reveal small pinkish regions where young stars ionize nearby gas. Older yellow stars gathered toward the center, and broad outer clouds detected more clearly by radio telescopes than by visible light. Astronomers study these features to ask whether galaxies grow differently when the surrounding cosmic web is thin. They measure stellar mass star formation activity, gas content, chemical enrichment, color, and shape. The results do not reduce easily to one universal portrait. Some studies find slightly enhanced star formation, relative to carefully selected comparison galaxies. Others find that galaxies of similar mass behave much alike across voids and ordinary low-density environments. Recent observations of molecular gas also suggest that void galaxies are not simply filled with an extraordinary supply of star-forming fuel. Their gas properties can resemble those of comparable galaxies elsewhere, even when subtler differences remain. This is scientifically useful. A disappointing stereotype can be an excellent result. It tells us that the large-scale environment influences galaxy growth without controlling every process inside it. Chemical composition provides another part of the story. Each generation of stars creates new elements and releases some of them back into the galaxy. Over time, repeated star formation and recycling enrich the gas from which later stars are born. A small void galaxy may have processed less material than a massive galaxy in a crowded region, and continued inflow of relatively unenriched gas may dilute its chemical abundance. Some observations and simulations therefore suggest that certain void galaxies can be less chemically enriched than comparable objects in denser structures. But again, stellar mass and local conditions must be separated carefully from the broad environment. A low-mass galaxy tends to contain fewer heavy elements, regardless of whether it resides in a void. Astronomers must compare like with like before, assigning the difference to cosmic geography. Even then, the environment is rarely a single switch. It operates through gas accretion merger history, nearby companions, and the dark matter halo surrounding the galaxy. The void shapes possibilities more often than outcomes. Our apparently solitary galaxy may not be as solitary as it first appeared. A small companion could orbit nearby, too dim to notice from a great distance. Another galaxy might lie along a faint chain extending through the void. Gas could be arriving from a structure containing few or no luminous stars. Void galaxies are sometimes found in pairs, small groups, and narrow arrangements, that hint at an internal architecture beneath the broader emptiness. A close encounter between two modest galaxies can compress gas and briefly increase star formation even when the nearest great cluster lies far beyond the horizon. This corrects another simple image. The interior of a void is not a collection of perfectly isolated islands distributed at random. The remaining galaxies still respond to local gravity, and local gravity can organize matter into subtle patterns. As we pull away from this faint system, more points begin to emerge, not enough to erase the darkness, but enough to suggest direction. Some appear loosely aligned, others gather around shallow concentrations of unseen mass. The great void may contain a smaller web of its own, delicate enough to remain hidden until we look more closely. The few galaxies ahead are not scattered as randomly as they first appeared. As our eyes adjust to the darkness, or more accurately as our imaginary instruments gather more light, several faint points begin to suggest a pattern. Two small galaxies lie along the same narrow direction. Farther on, another group follows the line separated from the first by a distance that would contain many large galaxies in a crowded region. A weak sheet of matter may extend away from them, almost invisible against the deeper underdensity. The great void has not disappeared. Its average density remains far below that of the surrounding cosmic web. Yet the interior is not smooth. On smaller scales, gravity has gathered some of the remaining material into delicate structures of its own. The cosmic web continues inside the void, but in a reduced and fragile form, like a drawing made with so little ink that its lines appear only after a long, patient look. A desert offers a useful comparison. Seen from high above it may appear broad, empty, and nearly featureless. Closer to the ground, the smooth surface divides into ridges, dry channels, isolated plants, and small changes in elevation. None of these local details turns the desert into a forest. They simply reveal that emptiness depends on the scale from which it is observed. Cosmic voids behave in a similar way. A region classified as underdense across tens or hundreds of millions of light-years may still contain smaller walls, filaments, galaxy pairs, and pockets that are emptier than the void around them. The comparison must not be carried too far. A cosmic void has no solid ground beneath it, and its structures are not carved by wind across a fixed landscape. They are three-dimensional arrangements of matter, shaped by gravity and expansion. Still, the changing viewpoint helps. From far away, we see a dark basin. From within, we begin to notice its terrain. This internal structure is part of a hierarchy extending across the universe. A large void can contain several smaller underdense regions separated by thin concentrations of matter. Those smaller regions may contain still finer variations. In computer simulations, astronomers can follow dark matter particles and watch this hierarchy emerge with remarkable clarity. Broad voids surround narrower sheets. Sheets meet in faint filaments. Filaments contain small dark matter halos, and some of those halos become the homes of galaxies. The process resembles the larger cosmic web, but the structures inside a void are generally less massive and more widely separated. They did not form in isolation from the surrounding universe. They are the remains of the same primordial pattern developed under conditions where there was less material available and less gravitational growth. The largest architecture dominates the map while the smaller framework survives quietly inside it. Nature, it seems, is quite fond of placing patterns inside larger versions of related patterns. It has never shown much interest in keeping the filing system simple. Observations offer hints of these faint internal filaments, although they are harder to map than their counterparts in dense regions. A bright filament between rich clusters may contain many galaxies, making its route easy to trace. A filament inside a void might be marked by only a handful of small galaxies spread across an enormous distance. One apparent line could be meaningful, or it could result from chance alignment, incomplete sampling, or the way three-dimensional positions are reconstructed from redshift measurements. Astronomers therefore compare observations with simulations and use statistical methods to decide whether a proposed structure is likely to be real. Some known systems of void galaxies appear embedded in narrow filamentary or wall-like arrangements rather than floating alone. These examples show that local gravity continues to organize matter even where the large-scale environment is sparse. They do not prove that every line of faint galaxies is a filament. The darker the region, the more careful the mapmaker must become. The dark matter halos inside these structures are important because they provide the gravitational foundations on which visible galaxies can form. Many halos may remain too small to produce a galaxy bright enough for present surveys to detect. Others may contain a dwarf galaxy with only a modest population of stars. This creates a difference between the web drawn by light and the web formed by mass. A galaxy survey may show 3 isolated points, while a simulation predicts a faint chain of dark halos connecting them. Some halos could contain gas but very few stars. Others may have lost or failed to collect enough ordinary matter to become visible at all. These possibilities are supported by models rather than by a complete observational inventory. Dark halos cannot simply be placed on a photograph as though they are dim lamps waiting for a longer exposure. Their presence must be inferred through gravity galaxy behavior, statistical comparisons, and the success or failure of cosmological simulations. Even the galaxies themselves may respond to their position within this smaller web. A galaxy resting in a faint internal filament can have a different local supply of matter and a different set of neighbours from one sitting near the deepest centre of a subvoid. Gas may approach preferentially along the filament. Small companions may form within the same line of dark matter halos. Interactions, though uncommon by the standards of crowded groups, can still occur. This means that the phrase void galaxy hides several environments inside it. One galaxy may be genuinely remote from any detected neighbour. Another may belong to a sparse pair. A third may occupy a thin structure crossing the broader void. Their large-scale address is similar, but their immediate surroundings are not. Separating these scales helps explain why studies of void galaxies sometimes find complicated or apparently conflicting results. The great void influences them all, while the smaller web gives each one a more private history. As we pull farther back, the interior now appears as a layered landscape. There is the great underdensity outlined by distant luminous walls. Inside it are smaller basins. Between those basins lie faint ridges, narrow galaxy alignments, and dark matter structures that may be only partly visible. Nothing here rivals the crowded richness of the main cosmic web, yet the darkness is no longer featureless. It contains organization without abundant structure, without brightness, and gravity working with the limited supply of material. But galaxies and dark halos account for only part of what remains. Between these sparse structures lies ordinary matter spread so thinly that it may leave almost no visible glow at all. To continue deeper, we must leave the remaining islands of starlight behind and enter the nearly transparent baryonic mist between them. Between the sparse galaxies, the void is filled with matter that is almost too thin to deserve a visible shape. We have left the faint internal filaments behind, but we have not entered perfect vacuum. Protons, electrons, atomic nuclei, photons, and traces of heavier elements remain scattered through the region. Most of this ordinary material is called baryonic matter, meaning the familiar matter that builds stars, planets, gas clouds, and eventually the bodies observing them. Here, however, it is not gathered into anything so convenient. It forms an extraordinarily diffuse intergalactic medium dominated by hydrogen and helium, much of it ionized so that electrons move separately from atomic nuclei. There may be no glowing cloud ahead, no mist visible around us, and no surface on which the material collects. The particles are simply spread through an immense volume. A void therefore contains a kind of atmosphere only in the loosest imaginable sense. It has material temperature and pressure but not enough density to behave like any atmosphere we've encountered near a planet. The word mist can help us picture this material, but it can also mislead us. An earthly mist is crowded with droplets that scatter light and hide distant objects. Gas inside a cosmic void is far thinner and may remain visually transparent across enormous distances. A better image might be a small drop of dye dispersed through a lake until no patch looks coloured, even though the dye has not ceased to exist. Even that comparison is far too dense. The important point is that matter can become difficult to see without becoming absent. Hydrogen in intergalactic space is often highly ionized by ultraviolet radiation from galaxies, quasars, and the wider cosmic background. With its electrons separated from its nuclei, it may produce very little ordinary visible light. Some of the gas can be relatively cool by cosmic standards, while other portions may be warmed by SHOX radiation or energetic material expelled from galaxies. The exact mixture varies with location and history. The void does not provide one uniform temperature because apparently empty places are allowed to be complicated too. Astronomers often detect this gas by allowing something brighter and more distant to shine through it. A quasar powered by matter falling toward a supermassive black hole can act like a lamp placed far behind the void. Its light begins with a broad spectrum of wavelengths. As that light travels toward Earth, atoms and ions along the path absorb very specific portions of it. When astronomers separate the arriving light into a spectrum, these missing wavelengths appear as narrow absorption lines. They can reveal hydrogen or heavier elements even when the gas itself produces no visible cloud. Only a small fraction of the hydrogen may remain neutral, but that fraction can still leave a detectable signature. The method is indirect and the geometry is limited. One quasar beam samples only one slender path through a vast three-dimensional region. It resembles examining an enormous dark landscape through a single drinking straw, although the straw in this case may extend across billions of light years. Useful certainly, comprehensive not quite. Some absorption systems appear to lie far from bright galaxies and within regions classified as cosmic voids. These observations show that ordinary gas can survive in deeply underdense environments. Yet assigning every absorber to a void is not simple. A faint galaxy may remain undetected nearby. A filament may cross the line of sight without being obvious in the available survey. The void boundary itself may shift when a deeper galaxy catalogue is used. Gas found inside the mapped region may also have originated elsewhere. Stars and active galactic nuclei can drive material out of galaxies carrying energy and chemically enriched gas into the surrounding intergalactic medium. Over immense periods, some expelled matter may reach low-density environments. Other gas may be more pristine, having avoided extensive processing inside stars and galaxies. Astronomers examine elements such as oxygen and carbon to investigate this history, because heavier elements were formed inside stars. Their presence can indicate that the material has already participated in the luminous universe, even when it now drifts through darkness. Computer simulations provide a broader view by following dark matter and ordinary gas through the growth of the cosmic web. In these modelled universes, baryons generally trace the same large structures as dark matter, but not perfectly. Gas can be heated, cooled, ionized, compressed, and expelled by energetic events. feedback from stars and black holes can move it away from galaxies, while gravity draws much of it toward filaments and halos. The interiors of voids remain depleted in baryons, just as they are depleted in total matter, but simulations predict that diffuse gas still threads through them. The gas may form shallow gradients, become slightly denser near internal filaments, or collect around the small halos supporting void galaxies. These models are valuable because they provide the three-dimensional information that observations cannot yet supply everywhere. They are not direct photographs of the actual void. Their predictions depend on the physical assumptions used to represent processes too small or complex to calculate in complete detail. A convincing simulation must eventually survive comparison with the real sky. New observing methods may gradually make that comparison stronger. Fast radio bursts, brief pulses of radio waves arriving from distant galaxies, travel through free electrons on their way to Earth. Those electrons delay lower radio frequencies slightly more than higher ones, creating a measurable effect called dispersion. If enough bursts pass through known voids, astronomers can compare their delays with sightlines through more typical regions and estimate whether the void contains fewer free electrons. The method does not require the gas to glow, and it is less concerned with whether the electrons belong to hot or cool material. Early measurements suggest that this approach may detect the expected baryon deficit, while confirming that diffuse ordinary matter remains inside the emptiest regions. The samples and models are still developing, so the results should not be treated as a finished census. But the principle is beautifully suited to the problem: use a distant pulse to notice particles that cannot otherwise be seen. The thin baryonic mist therefore gives us a more complete answer to what lies between the void's galaxies. There is ionized hydrogen and helium traces of heavier elements, radiation moving through the region, and gas whose temperature and density change across structures too faint for the eye. Some of it is revealed by absorption, some is suggested by simulations, some may be traced through the delays of radio signals. Much of it remains poorly mapped, especially near the deepest interior where useful background sources and visible foreground markers are limited. We cannot yet assign every baryon a location, and the universe has not supplied a convenient inventory label. Still, ordinary matter is only one layer of the unseen structure. Beneath the sparse gas lies a broader gravitational landscape, dominated by something that neither absorbs nor emits light in any familiar way. To descend further into the void, we must now follow the matter known mainly through the gravity it leaves behind. Dark matter does not disappear when we enter a cosmic void. It becomes sparse. Around galaxies and clusters, dark matter gathers into deep gravitational wells, providing most of the mass that holds those systems together. Inside the void, the landscape is shallower and quieter. There are fewer massive halos, less diffuse matter between them, and far less total mass than we would expect inside an equally large volume of the average universe. Yet the density does not fall neatly to zero. Dark matter particles still move through the region. Small halos remain around the faint galaxies we've already encountered. Other concentrations may be too modest to host visible galaxies at all. If ordinary cosmic structure resembles a mountainous landscape of clusters, groups, and filaments, then the void resembles a wide plain after the water has receded. Most of the mass is gathered elsewhere, but a thin and uneven residue still covers the ground. The tide is low. It has not removed the sea. The tidal image is useful because it suggests both absence and survival, but the physics is different. Dark matter was not washed out of the void by a current flowing from a distant ocean, nor was it blown away by an explosion at the center. The underdensity developed because matter was never distributed with perfect smoothness. Regions containing slightly more matter exerted slightly stronger gravitational attraction, and accumulated additional material. Regions containing slightly less matter grew more slowly and gradually lost matter to their denser surroundings. Dark matter followed this evolving gravitational landscape, helping build the walls and filaments around the void while leaving a reduced population behind. Some particles continued moving through the interior without belonging to a compact halo. Others became bound into small concentrations. The result is not a dark matter vacuum, but a broad deficit, deepest near much of the interior and generally rising toward the surrounding cosmic web. This invisible density profile gives the void its gravitational shape even where no galaxy conveniently marks the contours. The remaining halos are important because galaxies normally form inside them. A dark matter halo is a gravitationally bound concentration whose mass can draw in ordinary gas. If the halo becomes sufficiently massive, and if the gas can cool and remain available, stars may eventually form. Inside a void, fewer halos reach the large masses common near dense filaments and clusters. Many are expected to be small, reflecting the limited supply of matter and the slower growth of structure in an underdense environment. Some support dwarf galaxies. Some may contain gas and only a tiny stellar population. Others may remain effectively dark because star formation never began, became inefficient, or ended before enough stars accumulated to make the object detectable across cosmic distances. These dark or nearly dark halos are predicted by cosmological simulations, but they are difficult to identify individually. A halo without a luminous galaxy does not send us a polite notice of its location. Astronomers must look for indirect gravitational effects, or compare the statistical population of observed galaxies with the halo populations produced in modelled universes. This distinction creates two overlapping maps of the void. The first is drawn with light. It contains the galaxies measured by telescopes, each one serving as a visible tracer of structure. The second is drawn with total mass. It includes the dark halos around those galaxies, smaller halos with few or no stars, and diffuse dark matter spread between bound structures. The two maps should be related because galaxies grow within the dark matter distribution, but they need not match point for point. A survey using bright galaxies may identify a large, apparently vacant basin. A deeper survey may add dwarf galaxies to its interior. A simulation may then suggest that many more low-mass halos occupy the same region without becoming visible at all. This is why astronomers must be cautious when translating missing galaxies directly into missing mass. The void is genuinely underdense, but luminous objects provide only a sampled outline. They are lanterns placed across an invisible terrain, and some parts of that terrain contain no lanterns. Gravity offers a way to test the hidden map. As light from distant background galaxies passes through the universe, foreground matter bends its path slightly. Dense regions such as galaxy clusters produce a familiar weak lensing pattern associated with excess mass. A void creates the opposite kind of statistical signature compared with an average line of sight. There is less foreground matter available to bend the light. The effect from one void is extremely subtle, so astronomers usually combine measurements from many voids. By stacking them according to their estimated centers and sizes, they can search for a shared depression in the projected matter density. Such observations have detected the expected missing mass profile and have shown that voids identified through sparse galaxy distributions also correspond statistically to underdensities in total matter. This does not reveal individual dark matter particles or provide a detailed portrait of every halo. It weighs absence indirectly through the tiny distortions of more distant light. Even emptiness leaves a gravitational measurement. The dark matter interior remains partly a prediction rather than a complete census. Simulations can follow vast numbers of particles and show halo streams, density gradients, and matter flowing towards surrounding structures. Observations can test the average mass profile through lensing and examine the galaxies that occupy some of the predicted halos. But the smallest concentrations remain difficult to confirm, and the physical identity of dark matter itself is still unknown. We know what its gravity does far better than we know what the substance is. Within the void, that uncertainty feels especially clear. The dominant form of matter is present only in reduced amounts mapped through effects rather than light, and divided between structures we can partly trace and structures that may remain entirely dark. Yet its distribution is not arbitrary. It grew from the earliest variations in cosmic density. To understand why the void contains this shallow gravitational plane instead of a crowded range of halos, we must turn the clock backward toward a younger universe in which the great darkness began as a difference almost too small to notice. The great void began as something almost too small to notice. If we turn the cosmic clock backward, the dark matter plane around us grows denser, the surrounding filaments soften, and the galaxies dissolve into a younger universe that is far smoother than the one we know today. There are no mature clusters, no long luminous walls, and no immense dark basins waiting with finished boundaries. Matter is spread with remarkable uniformity, but it is not perfectly uniform. Some regions contain slightly more matter than the average, while others contain slightly less. These differences are tiny, yet gravity is patient. A small excess can attract additional material. A small deficit can fall behind as neighbouring regions grow. Over billions of years, the contrast becomes stronger. The crowded parts of the cosmic web and the quiet interiors of voids are therefore related from the beginning. One grows rich in matter, while the other becomes increasingly poor. The void is not a wound in the universe. It is the mature form of an ancient imbalance. Evidence for those early variations survives in the oldest light that astronomers can observe directly the cosmic microwave background. This radiation was released when the young universe cooled enough for light to travel freely through space. Across the sky, its temperature is almost uniform, but careful measurements reveal faint differences from one direction to another. These variations trace subtle changes in the density and motion of the early cosmic material. They are not photographs of today's individual galaxies or voids. They are more like the first gentle contours on a map that had not yet developed mountains, valleys, cities, or roads. The later cosmic web grew from this nearly smooth beginning. Denser regions became the seeds of clusters and filaments. Underdense regions became the seeds of voids. The pattern was present in outline long before stars began illuminating it. Darkness, in this case, had a history before there were lights available to define it. Imagine a broad field that appears almost level after a light rainfall. One patch is raised by only a small amount while another lies slightly lower. At first, the difference seems unimportant. As more rain falls, however, water collects more easily in the lower patch while the raised ground remains comparatively dry. A small initial variation gradually produces a larger contrast. Cosmic structure follows a related logic, although the direction of our comparison must be handled carefully. In the universe, gravity draws matter toward regions that already possess a little more mass strengthening the overdensities. Regions that begin with slightly less matter cannot compete as effectively for the surrounding material. They become increasingly underdense relative to the growing structures nearby. The analogy is limited because there is no solid field beneath the cosmos, no downward direction, and no rain falling from outside. Matter moves through expanding three-dimensional space under its own gravitational influence. Still, the simple lesson remains: small differences can grow when a process continually reinforces them. Expansion also plays an important role. The universe as a whole expands, carrying distant regions farther apart, but local gravity modifies how matter moves within that expansion. In a dense region, strong gravitational attraction slows the separation of matter and can eventually cause structures to collapse into halos, galaxies, and clusters. In an underdense region, gravity is weaker because less mass is present. Matter there is less able to resist the general expansion, while surrounding overdensities pull material outward in several directions. The void therefore expands relative to the denser cosmic web around it. This does not mean a mysterious substance at the center is pushing galaxies away. Nor does it mean the void grows by creating new space inside a rigid shell. Its growth is a change in the distribution of matter. The same collection of particles becomes spread across a larger region, while an increasing share of nearby material joins the walls and filaments outside. The darkness widens because the matter contrast deepens. At first, the underdense region may contain many modest concentrations of matter. Some become small halos and galaxies, others are stretched apart or drained toward denser surroundings. As time continues, neighboring underdensities can also merge. A thin wall separating them may lose matter until the distinction becomes weak, leaving one broader void where several smaller basins once existed. Yet the process is not identical everywhere. A small underdensity buried inside a large overdense region may eventually be compressed as the surrounding structure collapses. A large underdensity within a generally sparse environment is more likely to expand and join with nearby voids. This is one reason cosmic voids do not share a single shape or history. Some are broad and deep, some are shallow. Some possess crowded ridges. Some contain complicated internal webs left over from earlier stages. Their present appearance depends not only on their own initial deficit, but also on the larger environment in which that deficit grew. Computer simulations allow astronomers to watch this development in a controlled model universe. Researchers begin with early density variations consistent with observations include gravity and cosmic expansion, and follow the matter forward through time. Gradually the familiar network appears. Dense knots gather at filament intersections. Sheets and filaments sharpen. Between them, underdense regions enlarge, merge, and become more distinct. These simulations reproduce many broad features of the observed cosmic web, giving strong support to the idea that voids arise naturally from gravitational growth. But they do not provide a perfect biography of every real void. We cannot rewind one observed region and identify the exact position of each particle in its youth. Survey limits unknown small-scale details, and the assumptions of the cosmological model all restrict the reconstruction. We know the general mechanism far more confidently than the private history of any single basin. As the clock moves forward again, the smooth early universe gives way to the dark landscape we've been exploring. The faint initial deficit has widened into a region containing few galaxies, thin gas, small halos, and a shallow gravitational field. Around it, matter has gathered into brighter structures. The void did not appear suddenly, and nothing excavated it from the outside. It formed slowly because gravity amplified an ancient difference, allowing dense regions to become denser while the underdensity became increasingly empty by comparison. But this explanation opens another question. If the interior lost so much of its matter, where did that material actually go? And what paths did it follow as the void grew? To answer that, we must watch the movement itself, tracing matter away from the quiet center and toward the luminous boundaries beyond. The missing matter did not vanish. It moved. As the young under-density widened, particles within it continued to take part in the general expansion of the universe, but their local motion was also shaped by the uneven gravity around them. Denser regions beyond the void attracted matter more strongly than the sparse center could. Slowly, material drifted away from the deepest underdensity and toward the sheets, filaments, and clusters forming around it. The word drift may sound almost leisurely, and on human scales it would be. Across billions of years, however, a small persistent motion can reorganize an enormous region of space. Dark matter moved first in the sense that it dominated the gravitational framework. Ordinary gas followed that changing landscape, although pressure heating and feedback from galaxies complicated its path. Some matter joined the growing structures at the edge, some collected in the faint internal web, some remained diffuse. Nothing needed to be destroyed. The void became emptier because the surrounding universe became more successful at gathering what had once been spread through it. This motion is often described as an outflow from the void, but the phrase requires care. It does not mean that matter is being blown outward by a wind from the center. There is no hidden source of pressure and no repulsive object pushing galaxies away. The motion appears outward because the void is surrounded by denser destinations in many directions. Imagine standing in a broad valley while several towns grow along the surrounding hills. Roads work, and resources gradually draw people toward those towns, leaving the valley less populated. From the center, the movement seems to point outward everywhere, even though no force located in the valley is expelling anyone. Cosmic matter has no intentions and no roads, of course. It responds to gravity. But the comparison captures the geometry when denser structures lie around a sparse region. Gravitational attraction can direct matter away from the center toward the stronger concentrations beyond it. Astronomers separate this local motion from the overall expansion of space by using the idea of peculiar velocity. The name makes it sound eccentric, though the motion is perfectly respectable. Cosmic expansion gives distant regions a general tendency to separate. Peculiar velocity is the additional motion produced by local gravity. Near a galaxy cluster, peculiar velocities may point inward, because matter is falling toward the cluster. Around a large cosmic void, they often point away from the underdense center and toward the surrounding web. The two motions occur together. A galaxy near the rim is carried by cosmic expansion, while also moving relative to that expansion, because nearby structures pull on it unevenly. The result is not a simple radial flight from one exact central point. Real voids are irregular, and their surroundings are lopsided. Matter may flow more strongly toward a massive filament on one side than toward a weaker wall on another. The broad pattern is outward. The individual paths are more complicated. As matter leaves the interior, some of it accumulates near the boundary, helping build the ridge we crossed earlier. Dark matter collects into thicker sheets and filaments. Gas follows, becoming compressed and sometimes heated as it enters denser structures. Small halos merge into larger ones. Galaxies form, grow, and gather into groups. Seen over cosmic time, the void and its rim evolve as one connected system. The interior loses density while the surrounding network gains contrast. This does not mean that every particle originally inside the void ends up neatly arranged along one shell. Many travel toward different structures. Some pass through the rim and continue into filaments. Others remain in low-mass halos or diffuse streams. The raised boundary seen in an average density profile is therefore a statistical pattern, not a warehouse containing all the matter that once occupied the center. Cosmic bookkeeping is rarely that accommodating. There is also a limit to how empty the center can become. As the density falls, less matter remains available to remove and the growth of the contrast changes. The void continues expanding relative to dense structures, but its interior is not drained like water through a plug. Particles still cross the region. Small halos continue orbiting within the larger gravitational landscape. Gas can enter along one direction even while the average flow points outward. Neighbouring voids may merge when the weak structures between them lose enough matter, creating a wider basin whose centre is not identical to either earlier centre. Meanwhile, the walls and filaments around the void continue evolving under their own gravity. The system has no permanent border and no final arrangement. It is a slowly changing pattern of density and motion, drawn across expanding space. Astronomers can look for this motion in galaxy surveys. A galaxy's redshift contains information about cosmic expansion, but its peculiar velocity also alters the measurement slightly. When many galaxies around many voids are studied together, these additional motions can distort the apparent shape of the void in redshift space. A roughly rounded underdensity may appear stretched or compressed along the observer's line of sight, depending on the velocity pattern and the way the void was selected. By comparing these distortions with cosmological models, researchers can estimate how galaxies move around voids and how quickly large-scale structure has grown. The measurement is delicate. Galaxy positions are incomplete, void centers are uncertain, and several effects overlap. Yet the broad evidence agrees with the physical picture. Matter around large underdensities tends to move away from their interiors and toward denser surroundings. The void can be read not only as a shortage of galaxies, but also as a pattern of motion. From our position inside the darkness, the destination of the missing matter is now visible in every direction. It is present in the distant ridge in the filaments extending beyond it, in galaxy groups collecting along the web, and in clusters growing where several structures meet. Some of that matter may once have occupied regions now classified as part of the void. Some began closer to the boundaries. Some never entered the underdensity at all. There is no simple ledger assigning each particle a former address. What we can say is gentler and more accurate. The void became sparse because gravity gave matter better places to gather. Its emptiness and the brightness around it are two sides of the same history. And as the material continued moving, the void itself did not remain unchanged. Some underdensities widened and joined their neighbours. Others were squeezed by the dense environments around them. The next stage of our journey is therefore not about what left, but about what became of the space it left behind. A cosmic void is not guaranteed a quiet and endless future. Its fate depends on the larger landscape around it. Some underdense regions continue expanding relative to the cosmic web growing broader as matter drains toward distant walls and filaments. Others become part of still larger voids, their separate identities fading as the thin structures between them weaken. And some small underdensities lie inside environments so crowded that the surrounding gravity begins to squeeze them. The same lack of matter can therefore lead to very different histories. To understand why, we must step back from the individual void and examine its address on a larger map. Is it nested inside another broad underdensity with sparse space extending far beyond its rim, or is it a small pocket surrounded by a massive wall filament or collapsing concentration of matter? A void does not evolve by consulting its own interior alone. The universe around it has a vote, and the surrounding matter is usually better represented at the meeting. Consider first a void embedded within a still larger underdense region. Astronomers sometimes describe this as a void-in-void system. This smaller basin expands along with its sparse surroundings, while matter continues moving towards structures farther away. Nearby underdensities may also grow separated at first by thin walls or weak filaments. Over time, those dividing structures can lose material, Their density falls, their gravitational importance weakens, and the distinction between neighbouring basins becomes less pronounced. What once appeared as several separate voids may eventually be classified as sub-regions of one larger underdensity. It is tempting to picture soap bubbles merging their membranes opening until a larger bubble remains. Visually, the comparison is helpful. Physically, it must be treated gently. Cosmic voids have no membranes to break, no enclosed gas pressing against a surface, and no sharp moment of contact. Their merger is the gradual fading of a density ridge until two underdense regions belong to one connected landscape. Even the word merger may suggest more drama than the process usually deserves. Galaxies do not rush toward one another at the centres of the voids. There is no collision between two hollow objects. Instead, the boundary used to distinguish the regions becomes less meaningful. Imagine two broad valleys separated by a low ridge. If erosion gradually lowers that ridge, the valleys may come to form one wider basin, although the older depressions can remain visible as smaller features within it. A large cosmic void can preserve a similar hierarchy. Earlier underdensities survive as subvoids, while the parent region becomes the dominant structure on the map. Simulations that trace voids through cosmic time often show surprisingly stable identities, with many smaller voids becoming nested inside larger ones rather than vanishing in a sudden event. Their centres may shift only modestly, and their growth can proceed more quietly than the turbulent merger histories of massive dark matter halos. Voids are large transformations carried out with very little theatrical assistance. A different history awaits a small void located inside a broadly overdense environment. This is the idea known as void in cloud evolution. Here the surrounding region contains more matter than average, and may be contracting gravitationally, or assembling into a dense filament group or cluster. The small underdensity initially tries to expand, but the larger environment presses inward. Matter outside it moves toward the collapsing overdensity, and the void can be compressed, distorted, or partly erased. Picture a soft depression in a cushion while the entire cushion is being squeezed from both sides. The depression may narrow even though it began as a low region. Again, the comparison has limits. A cosmic void is not made of elastic material, and the compression is rarely equal from every direction. Tidal forces from surrounding structures can stretch the void along one axis and squeeze it along another, producing an irregular evolution rather than a neat spherical collapse. The simplest analytical models describe small voids in dense environments as being crushed out of existence. Real simulations reveal a more complicated picture. Some small underdensities do contract, but others are only partly compressed. They may become shallower, elongated, or incorporated into the structure surrounding them without losing every trace of their earlier identity. The outcome depends on scale-shape tidal environment and the method used to define the void. A spherical model may predict one clean fate, while an irregular region threaded between several evolving structures follows a less cooperative path. This does not make the simpler model useless. It provides a basic framework for understanding why small voids are less common in strongly overdense surroundings, and why the population of cosmic voids changes with scale. But the model is a map of tendencies, not a diary of every region. Small voids, like small objects, generally, often live complicated lives beneath the resolution of a broad theory. Growth also changes the shape of a surviving void. As matter continues leaving the interior, its central density can become broadly low and relatively flat, while the transition near the edge becomes steeper. Surrounding ridges may sharpen as material collects there, yet the void rarely remains spherical. Nearby clusters pull more strongly than modest filaments. Adjacent voids open easier routes for expansion than dense walls. The underdensity can stretch into an elongated basin, branch around a filament, or join a wider network of low-density corridors. Some regions classified as one void by a watershed method may contain several internal centers, while a spherical search may divide the same landscape differently. Evolution and definition therefore remain linked. When the shape changes, the catalogue may change with it. A void can appear, merge, divide, or disappear partly because the physical density field evolved, and partly because our chosen boundaries no longer describe it in the same way. From far above the cosmic web we can now watch both destinies unfold. In one direction, neighbouring dark basins expand and become connected as the faint ridge between them drains away. In another, a small underdensity is caught inside a growing concentration of matter, its shape narrowing as the surrounding structure strengthens. Neither process requires a physical wall, and neither ends with a completely empty cavity. What changes is the distribution of matter and the scale at which we name the resulting pattern. Large voids can grow into dominant features of the web. Smaller ones may survive as nested subvoids become distorted or fade into denser surroundings. Their lives are slow, irregular, and inseparable from the structures around them. Yet we do not watch this evolution from outside the universe with a perfect view. Astronomers receive scattered galaxies, measured redshifts, incomplete survey volumes, and mathematical definitions. To follow a void's life, they must first solve a quieter problem: how to find and catalogue something whose most obvious feature is that so little appears to be there. A cosmic void is easiest to recognize only after a map has already been built. From inside one, the view would not resemble a dark sphere with a visible edge. It would contain a few nearby galaxies, many distant galaxies beyond the surrounding walls, and an enormous amount of darkness in every direction. The void would not label itself. Astronomers therefore begin with something more manageable: the light of individual galaxies. They record where each galaxy appears on the sky, then measure how much its spectrum has been shifted toward longer wavelengths. Most of that redshift reflects the expansion of the universe, so it provides an estimate of distance. Repeating the process for hundreds of thousands or millions of galaxies turns a flat sky map into a three-dimensional distribution. Bright knots become clusters, long concentrations become filaments and walls. Between them, regions with unusually few measured galaxies begin to emerge. Only then can absence acquire coordinates. The method resembles building a landscape from scattered altitude markers. Imagine an enormous country hidden beneath darkness, with surveyors able to measure the elevation at isolated points, but unable to walk every field and valley. From enough measurements they could reconstruct hills, ridges, and low basins. Galaxy surveys perform a related task, except their markers are luminous objects spread through expanding space. Dense collections of galaxies outline the high regions of the cosmic web. Sparse regions suggest the basins. The analogy is useful, but the cosmic map has an added difficulty. Galaxies are not neutral measuring posts. They form more readily in some kinds of dark matter halos than others, and the brightest galaxies trace dense environments differently from faint dwarf systems. The map is therefore shaped partly by the matter distribution, and partly by the population chosen to represent it. Change the markers and some details of the landscape change with them. Once a survey has produced its three-dimensional points, astronomers still need a rule for deciding which sparse regions count as voids. One approach searches for large, nearly spherical volumes containing very few galaxies. The algorithm may expand an empty sphere until it approaches the nearest traces, then record its center and radius. This produces voids that are easy to describe and compare, but the universe rarely arranges its underdensities as perfect balls, A real void may curve around a filament stretch between two clusters or contain several internal depressions. A spherical catalogue can therefore capture the quietest central regions while overlooking their irregular extensions. The advantage is clarity. The limitation is geometry. A sphere is a convenient answer to a complicated landscape, rather like describing an entire coastline with one well-behaved circle. The calculation becomes simpler. The coast remains unconvinced. Another family of methods treats the galaxy distribution as a topographic surface. Regions around individual galaxies are assigned volumes according to how closely neighbouring traces are packed. Sparse areas become low-density zones. An algorithm then follows the density upward from those zones until neighbouring basins meet at a ridge. This is often compared with water collecting in valleys, which is why such techniques are described as watershed methods. Several small basins may be combined into a larger void when the ridge between them is sufficiently weak. The resulting shapes can follow the irregular architecture of the cosmic web more naturally than spheres do. Yet the result depends on decisions about which basins should be joined, which density threshold should be used, and how survey boundaries are handled. Two catalogues can examine the same galaxies and divide the underdense landscape differently. They may disagree about the number of voids without disagreeing that the region is sparse. The measurements themselves also distort the map. Redshift gives distance only after astronomers account for the fact that galaxies possess peculiar velocities in addition to taking part in cosmic expansion. Near a void, galaxies tend to move relative to the expansion as they respond to surrounding structures. That additional motion changes the observed redshift slightly. When positions are reconstructed, a void can appear stretched or compressed along the observer's line of sight. This is known as a redshift space distortion. It is both a complication and a source of information. The distortion can interfere with attempts to recover the void's true shape, but its pattern also contains clues about how matter is moving and how rapidly large-scale structure has grown. Astronomers must model the effect rather than simply remove it as an error. The map is distorted because the universe is moving, and the movement is part of the story. Survey limits create further uncertainty. A telescope may observe only part of the sky, leaving artificial edges where no galaxies were measured. Bright stars in our own galaxy can hide regions behind them. Faint distant galaxies may fall below the detection threshold. The farther a survey reaches, the more strongly its sample may favour only the brightest objects. A region near the edge of the catalogue can appear empty because the telescope did not look beyond it, not because a physical void ends there. Modern analyses use masks, random comparison catalogues, completeness corrections, and mock surveys built from simulations to estimate these effects. Even so, a void catalogue is not a simple list of objects waiting unchanged in nature. It is the result of observation, selection rules, mathematical definitions, and quality checks. This does not make the voids unreal. It tells us exactly what kind of evidence supports them. For this reason, astronomers rarely ask whether one catalogue has discovered the only correct set of voids. Instead, they ask whether a chosen definition is suitable for a particular scientific question. Nearly spherical voids may be convenient for measuring average radial profiles. Watershed voids may better preserve the connected geometry of underdense regions. Voids traced by bright galaxies may cover larger apparent volumes than those traced by a denser population of faint galaxies. Voids found directly in simulations can be defined using dark matter or total mass rather than light. Each catalogue becomes an instrument designed to emphasize certain features. The safest conclusions are those that remain stable when researchers vary the tracer's methods and assumptions. A void is therefore measured not by pretending that absence is simple, but by showing that the underdensity persists under careful comparison. We can now imagine the final map floating before us. Every luminous point came from a measured galaxy. Every distance was reconstructed from light stretched by expansion and local motion. Every void boundary was drawn by a rule that could be stated, tested, and repeated. The dark basin is real, but its exact center and rim depend on the question being asked. Galaxy maps reveal where visible traces are missing. They do not yet prove how much total matter lies beneath that absence. To move from a catalogue of sparse lights to a measurement of missing mass, astronomers need another messenger, one that responds to gravity whether matter shines or remains dark. The next step is to watch distant light pass the void and notice how slightly the darkness bends it. A void can be weighed without placing anything inside it. We have already used galaxies to mark the underdensity, but galaxies reveal only where luminous traces are sparse. To learn whether the total mass is also reduced, astronomers turn to light arriving from much farther away. Every beam crossing the universe follows the geometry created by matter along its path. A massive galaxy cluster bends those paths enough to stretch the images of background galaxies into a coordinated pattern. A cosmic void produces a subtler counterpart. Because it contains less matter than an average region, its gravitational influence differs from that of the surrounding universe. The distant images are altered slightly, not because the void contains negative mass or pushes light outward, but because the usual foreground mass is partly missing. This signal is weak. The principle is simple. Gravity allows the darkness to be measured through what it does not bend in quite the ordinary way. Imagine looking through a pane of glass so gently warped that one object behind it gives no obvious clue. Its shape might be naturally oval or slightly tilted for reasons unrelated to the glass. Place thousands of objects behind the same kind of distortion, however, and a shared pattern can emerge. Weak gravitational lensing works in a related way. Background galaxies already possess many intrinsic shapes and orientations. Astronomers cannot examine a single image and confidently separate its natural form from the tiny lensing distortion added during the journey to Earth. Instead, they measure large populations. Random orientations tend to average away while a coherent gravitational pattern remains. For an overdense object, the images commonly show a statistical tangential alignment around the foreground mass. Around a void, the pattern changes sign in the mathematical description, reflecting the deficit of projected matter. No individual galaxy announces the measurement. The answer appears only when many quiet imperfections are considered together. One void is usually not enough. Its lensing effect competes with the natural diversity of background galaxies' measurement noise, unrelated structures along the line of sight and uncertainty in the void's center and shape. Astronomers therefore stack many voids. They rescale them by an estimated radius, align their centers, and combine the shapes of background galaxies seen behind all of them. The procedure treats the collection as though it were one average void observed many times. Irregular details fade while the common mass profile becomes easier to detect. Stacking is powerful, but it changes the question. It does not weigh each individual void precisely. It measures the average gravitational signature of a selected population. If small and large voids have different structures, mixing them can blur the result. If some possess dense surrounding ridges and others do not, their lensing patterns may differ. The emptiness must be sorted before it can be added together. Even nothing, statistically speaking, requires careful filing. The measurement is often expressed as a difference in projected surface mass density. Lensing records all the matter integrated along the line of sight, rather than producing a direct three-dimensional scan. Dark matter contributes. Diffuse gas contributes. Galaxies and their halos contribute. Structures lying in front of or behind the void can also contribute even when they are not physically part of it. Researchers use models and comparison catalogues to separate the average void signal from this surrounding cosmic clutter. They then infer how the density changes with distance from the estimated center. A typical stacked profile may show a mass deficit through the interior, and for some void populations arise near the rim where matter has accumulated. The ridge matters. A model containing only an empty central sphere can misread the lensing pattern, created by the underdense interior and denser boundary together. The void is weighed as a landscape, not as an isolated whole. Several effects can blur this landscape. A catalogue center based on surrounding galaxies may not coincide with the lowest point in the true matter density. When many such voids are stacked, that miscentering softens the central signal. Their irregular three-dimensional shapes are projected onto the flat sky, so different orientations produce different apparent profiles. The redshifts of foreground voids and background sources carry uncertainties, and a galaxy mistakenly placed in front of the lens cannot provide the intended measurement. The shapes of background galaxies must also be calibrated with extraordinary care because small biases can imitate or conceal weak lensing. Unrelated large-scale structure along the sightline adds further distortion. None of these problems makes the method impossible. They explain why the result is statistical, why simulations are used to test the analysis, and why stronger measurements require wide surveys containing many voids and enormous numbers of well-measured galaxies. Lensing can be compared with a galaxy map that identified the void. If the sparse distribution of visible galaxies follows the underlying matter reasonably well on these scales, then the galaxy profile and lensing-derived matter profile should display related shapes after the appropriate bias is considered. Agreement supports the idea that luminous traces outline a real deficit in total mass. Differences may reveal how galaxies occupy dark matter structures, how the void sample was selected, or whether modeling needs improvement. Other messengers provide complementary views. The motions of galaxies around voids distort their redshift space pattern, revealing how gravity guides matter towards surrounding structures. Maps of the cosmic microwave background can also be gravitationally lensed by the matter distribution between that ancient light and us, offering another projected view of cosmic mass. Each technique sees the void differently. Together they turn a dark gap in a galaxy catalogue into a physical region with measurable density, motion, and gravitational influence. We can now look back across the basin and understand what it means to lens the darkness. The void does not bend light strongly like a massive cluster, nor does it behave as though gravity has reversed. It changes the lensing pattern because less mass occupies the region than would normally lie along a comparable path. By combining many faint background images, astronomers can detect that deficit and estimate how it varies from the interior to the surrounding ridge. The method includes luminous and dark matter without requiring either to shine, but it remains an average reconstruction shaped by projection selection and modelling. It shows that the void is not merely a shortage of visible galaxies, it is a genuine depression in the larger matter field. And once that depression can be measured, the void becomes more than an object to describe. Its size, shape, density, and motion can be used to test how the entire universe has grown. A cosmic void becomes most useful when we stop treating it as merely an empty place. Its low density makes it a different kind of laboratory from a galaxy cluster. Clusters show gravity working where matter is abundant, crowded, hot, and deeply bound. Voids show the same universe where matter is scarce. Gravitational wells are shallow, and expansion has faced less local resistance. Both environments grew from the same early density variations and obey the same underlying physical laws, but they emphasize different parts of those laws. Studying only clusters would be like testing a machine only while it carries its heaviest load. Studying voids asks how the machine behaves when the load is almost gone. The equipment in this laboratory is inconveniently large. The experiment has been running for billions of years and no one remembered to include an off switch. Still, the measurements are real. The sizes, shapes, populations, density, profiles, motions, and lensing signatures of voids preserve information about how cosmic structure developed. One of the broadest questions concerns dark energy, the name given to whatever is causing the expansion of the universe to accelerate. Dark energy does not need to gather at the center of a void for the void to become useful. In the simplest cosmological model, it is distributed smoothly and influences expansion everywhere. Dense regions partly resist expansion through their own gravity, while underdense regions contain less matter to provide that resistance. Voids therefore respond sensitively to the balance between cosmic expansion and the growth of structure. If expansion accelerates earlier or more strongly, matter has less time to gather, and the population of voids can change. Their abundance, typical sizes, surrounding ridges, and rates of growth may all carry part of that history. Astronomers compare observed void catalogues with simulated universes built using different expansion histories. The goal is not to locate dark energy as though it were a hidden gas inside the emptiness. It is to examine how the emptiness evolved under the expansion that dark energy appears to govern. The apparent shapes of voids can provide another test. There is no reason for a large collection of voids to point preferentially toward Earth. Individually, they are irregular, stretched by nearby structures, and difficult to interpret. But after many are combined, their average orientation should be statistically balanced. If astronomers assume the wrong relationship between redshift and distance when constructing the three-dimensional map, the stacked voids can appear systematically stretched or compressed along the line of sight. This geometric comparison can help test the expansion history of the universe. At the same time, peculiar velocities create their own redshift space distortions, because galaxies around voids are moving relative to the general expansion. Geometry and motion must therefore be modelled together. A distorted void may reflect an incorrect cosmological distance scale, the genuine flow of matter, catalogue selection, or several effects at once. The method is promising precisely because it is sensitive. Sensitivity, however, is simply another word for requiring great care. Voids may also test whether gravity behaves exactly as general relativity predicts on the larger scales. Some alternative theories introduce additional fields or forces designed to reproduce cosmic acceleration without a conventional dark energy component. In dense environments, these extra effects may be hidden by screening mechanisms allowing gravity to look nearly ordinary around galaxies, stars, and planets. Low-density regions can provide less screening, making voids potentially sensitive places to search for deviations. Modified gravity might alter how quickly matter leaves an underdensity, how steeply density rises toward its edge, how galaxies move around it, or how strongly the region lenses background light. But no single unusual profile would establish a new theory of gravity. The same signal might arise from galaxy bias, survey limitations, neutrino effects, or imperfect modelling of ordinary cosmology. Researchers must test several observables together and compare them across independent surveys. A void is a clean environment only in the sense that it contains little matter. Scientifically, it still comes with a respectable amount of paperwork. Even particles that barely interact with ordinary matter can leave a trace in the void population. Neutrinos are extraordinarily light, but they exist in vast numbers and move rapidly through the universe. Because they stream out of smaller concentrations rather than clustering as efficiently as cold dark matter, they can slow the growth of structure on certain scales. This may influence the number of small halos, the development of filaments, and the abundance and density profiles of voids. Different neutrino masses can produce subtly different cosmic webs in simulations. The effect is not a bright signature waiting at the center of one enormous void. It appears statistically across many regions and overlaps with changes caused by other cosmological parameters. The same caution applies to possible properties of dark matter. If dark matter is warmer, self-interacting, or otherwise different from the simplest cold dark matter model, the populations of small halos and faint galaxies inside voids might change. Yet these possibilities remain tests, not discoveries. The darkness offers sensitivity, not automatic certainty. The strongest approach is therefore to combine many measurements. Galaxy surveys provide the positions and apparent shapes of voids. Redshift space distortions trace the motions around them. Weak gravitational lensing measures their average deficit of total mass. The cosmic microwave background can provide additional lensing information and may contain weak secondary signatures related to the evolution of gravitational potentials along the line of sight. Void galaxies reveal how luminous matter behaves in sparse environments. Simulations connect these observables to different physical models. Each measurement has limitations, but their weaknesses are not identical. A model that matches the number of voids yet fails to reproduce their lensing profile is incomplete. A theory that predicts the correct density but the wrong galaxy velocities faces another test. Agreement across several independent signals is far more persuasive than an anomaly in one catalogue. From this wider perspective, the Great Void is no longer merely a destination on our journey. It is an instrument shaped by cosmic history. Its interior records how matter failed to gather. Its rim records where some of that matter went. Its galaxies reveal what structure can grow with limited material. Its lensing profile measures the mass that is missing, while the motions around it reveal how gravity and expansion have competed over time. Future surveys will map more voids, trace fainter galaxies, measure background shapes more accurately, and compare larger volumes of the universe. They may tighten our understanding of dark energy neutrinos' gravity, and the relationship between galaxies and dark matter. They may also show that the standard cosmological model continues to describe the evidence remarkably well. Science must allow both outcomes. The quietest regions are valuable not because they promise a hidden revolution, but because they provide a different and unusually sensitive way to ask familiar questions. We have now used the void as a map, a history, a gravitational landscape, and a laboratory. One final question remains. After all these layers have been uncovered, what can we responsibly say truly lies inside it? So what lies inside the great cosmic void? The clearest answer is not nothing. Inside are faint galaxies separated by immense distances. Small groups and delicate filaments diffuse hydrogen, and helium traces of heavier elements, low-mass dark matter, halos, radiation crossing the region, and particles moving through a gravitational landscape far shallower than the one surrounding a cluster. There is less of almost everything that gathers into visible structure, but less is not the same as none. The void is a deficit measured against the average universe. Its darkness comes partly from the small number of stars available to illuminate it, and partly from the enormous spaces between the structures that remain. From our imagined position near its centre, the luminous walls now lie far away, forming a dim and irregular horizon. Yet even here gravity still acts, gas still responds to radiation, galaxies still form stars, and the expansion of the universe continues. The region is quiet by cosmic standards, it is not inactive. Some parts of this answer are well established. Galaxy surveys show that large underdense regions occupy the spaces between the denser walls and filaments of the cosmic web. Telescopes have observed galaxies within those regions, including small systems that continue forming stars. Absorption lines reveal diffuse gas along sight lines passing through sparse environments. Weak gravitational lensing shows statistically that galaxy-defined voids correspond to real deficits in total mass. Measurements of galaxy positions and redshifts also reveal patterns of motion around them, consistent with matter moving away from underdense interiors and towards surrounding structures. None of these observations requires a hidden force pushing from the center. The same gravity that gathers matter into clusters helps empty the regions between them. A void and its luminous rim are therefore not separate accidents. They are connected results of the same long process. Matter collected more effectively in one place, leaving less behind in another. Other details are supported more strongly by models than by direct inventories. Simulations suggest that many low-mass dark matter halos may remain inside voids, including halos too small or too poor in gas to contain visible galaxies. They suggest that the apparently smooth darkness may hold a faint hierarchy of subvoids, narrow sheets and miniature filaments. They also help reconstruct how an almost imperceptible early underdensity could expand, merge with neighboring underdensities, and develop the broad profile observed today. These modeled universes reproduce many features of the cosmic web which give scientists confidence in the general picture. But a simulation is not a photograph of the actual void before us. It begins with measured conditions and known physical laws, then calculates what should follow. Its value comes from comparison with observations. Where the two agree, the explanation becomes stronger. Where they differ, the disagreement becomes a question rather than an invitation to quietly replace evidence with imagination, and much remains unknown. Astronomers cannot yet count every dwarf galaxy hidden below present detection limits. They cannot map every strand of gas throughout a void's full three-dimensional volume. The smallest dark matter halos may remain entirely invisible, and the particle nature of dark matter itself is still unresolved. Even the exact boundary of the void depends on which galaxies were measured and which mathematical definition was used. Different surveys may divide one underdense landscape into different basins without disagreeing about its broad physical reality. We also do not yet know whether future measurements of void abundance, lensing motion and shape will reveal new physics or simply sharpen the standard cosmological model. Dark energy has not been found pooled inside these regions. Modified gravity has not been confirmed there. The void is valuable because it provides a sensitive test, not because every unanswered question is secretly hiding at its center. The image from the beginning can now return. We first saw a great dark basin surrounded by luminous ridges apparently cut from the cosmic web. After travelling through it, the basin is no longer blank. A few galaxies mark its interior. Fainter structures connect some of them. Thin ordinary matter drifts between the lights, while dark matter gives the region a shallow, uneven gravitational form. Around the edge, denser walls preserve some of the material that gathered away from the center. The void shape is therefore made from both what remains and what is missing. A pause in music offers a gentle comparison. The pause contains no played note, yet its position changes the meaning of the notes around it. A cosmic void is not an artistic silence, and was not placed deliberately, but its absence also belongs to a larger structure. Remove the voids and the cosmic web would no longer have the same shape. We can now pull away from the dark basin. Its few internal galaxies shrink into faint points. The surrounding rim becomes part of a broader filament, and that filament joins countless others crossing the observable universe. Farther back, the cosmic web becomes too large and delicate to see from any ordinary human viewpoint. The Milky Way returns as one galaxy among many, then as the familiar band of light beyond the window. The room around you has remained safe and still throughout the journey. Somewhere beyond its walls, the universe continues arranging matter into bright gatherings and quiet intervals, each helping define the other. The great cosmic void is not a hole where the universe failed to exist. It is one of the forms the universe took as gravity shaped an uneven beginning. Its emptiness has structure, its silence has history. And the questions that remain do not need to be solved tonight. They can stay far beyond the window while the room grows quiet. The stars continue without attention, and you allow yourself to rest.